What is mass? All fundamental particles, in and of themselves, are massless. If you just had an electron with nothing else in the universe, it would be massless. If you just had a quark, the subatomic particles that make up protons and neutrons, on its own, it would be massless. So, how is it that these particles, which would be massless on their own, can gain mass? Well, essentially, inertial mass is a property that arises when massless particles are restricted from moving freely through space. Let me elaborate. Imagine you have a hypothetical massless box. I weigh this massless box and it weighs nothing. It is massless. If I add some massless particles to this massless box, then weigh it, I will measure some mass. It appears like the confining of the particles inside the box, the restriction of their movement, caused the box to have mass. And that's because it did. This is inertial mass. It is the restriction of massless particles from moving freely. Are we sure about this? Well, let's have a look at a well-known property of mass. Mass resists acceleration. So imagine my box has two particles in it, randomly moving around and bouncing off the walls. For simplicity, I'm going to say one is moving to the left and one to the right, just to make things simpler. If no external force is placed on the box, then on average, the particles will bounce off the sides of the walls equally and with equal force, and so the box will not change velocity. However, if I apply a force to the box, say I push it to your right, then the force that the particle moving in the direction of the push has when it hits the wall will be less than the force that the particle moving against the direction of the push has. Why is this? Well, to find the impact velocity of the particle moving with the push, we must take the particle's speed, let's say it's 20 whatevers, and minus the speed of the push, because they're moving in the same direction. So let's say the speed of the push is 10. So 20 minus 10 equals 10. So this gives us a total velocity for this particle, an impact velocity of 10. Whereas the impact velocity of the particle moving against the push, let's say again its speed is 20, would be 20 add 10, which equals 30, as they're heading towards each other. Therefore, the force exerted by the particles moving against the direction of the force is greater than the force exerted by the particle moving in the direction of the force. Thus, the push is resisted. Accelerating the box is harder than if we had an empty box. The inertial mass is greater. And the more particles, well, strictly speaking energy, in the box, the harder the acceleration. That's why boxes with more particles have a higher mass. It's why when I kick an elephant and I kick a mouse, the mouse accelerates more. Squeak. Obviously, don't kick animals. The mouse has less particles in the box resisting my external force. This even applies to photons of light trapped in a box. If I made these particles light photons and measured the mass of this box, I would record mass. So, this has all been very abstract so far, with talk of this magical massless box. Let's apply this to an actual system. A proton consists of 2 up and 1 down quark. These quarks are held together by the strong nuclear force. Now, the thing about the strong nuclear force is, unlike gravity, it gets stronger the further away the quarks get. People often represent it as a spring. The more you stretch the spring, the more it wants to ping back. This is an example of our massless box. The quarks cannot leave the box because the strong nuclear force would pull them back in. And in fact, we actually never ever see quarks not locked up in either pairs or triplets like this, a phenomenon called confinement. So it very much is a box. If this quark tries to go too far in this direction, the strong nuclear force will pull it back in. And the same for any other quark going in any other direction. So the quarks are very much confined by the strong nuclear force. This is the box. When I talk about the quarks hitting the wall of the box, what that would mean in this circumstance is the quark moving in this direction against the strong nuclear force. And there are many more examples like this. Okay, so what about an ionized electron? An electron that has left the atom. An ionized electron is just an electron, right? There are no protons or neutrons. Ionized electrons still have mass, roughly 1/1840th of a proton. But they aren't being restricted from moving through space, are they? I mean, they're no longer held around the nucleus by the proton's positive charge. So where is the restriction in movement in an ionized electron? Aren't they just zipping freely through space? Well, this is where the Higgs field comes in. To understand how this works, we have to think about the wave-particle duality of matter. One model of thinking of matter is as particles, but a just as correct model of thinking about matter is as waves. Electrons, quarks, light is all made out of different types of waves. Now, if we map out the size or amplitude of these waves over the whole of space, we get what's called a field. The field just tells us the amplitude of the wave at every position in space. And each type of particle has its own field. There is an electron field, for example. So here I've just shown the amplitude, I've said energy, which may not strictly be true, amplitude energy, and then I've just shown 2 directions of space. Now, the electron field fluctuates around 0. The reason it fluctuates, by the way, is something called the Heisenberg uncertainty principle, which is proper cool, you should definitely check it out. Every now and again, there will be a big wiggle in the field, where the field has more energy, more amplitude. That represents a particle of an electron. But the important thing to remember is it fluctuates around 0. The really weird thing is that a Higgs field does not fluctuate around 0. It fluctuates around 1. And so the whole of space is permeated with a non-zero Higgs field. There is Higgs field in you right now. Okay, so let's get back to our ionized electron. It turns out that electrons can come in 2 forms, 2 different chiralities, what we call left-handed and right-handed. And another proper weird thing is that these 2 chiralities are not identical. One of them has something called a weak hypercharge, which the other does not. As the electron zips through space, it can interact with the Higgs field, which remember permeates all of space with roughly a value of 1, and through this interaction both lose or gain the weak hypercharge. and so flip between left-handed and right-handed forms. So even an ionized electron moving freely, in commas, through space is being buffeted at all times, or restricted from moving freely by its interaction with the Higgs field. And so even an ionized electron will have mass. People often say the Higgs boson causes mass. The Higgs boson, which is just a particle of Higgs, has nothing to do with creating mass. It's just that the Higgs field is almost impossible to detect directly. But by looking for the Higgs boson, which is the bump in the Higgs field, which represents a particle of Higgs, we can prove that the Higgs field must be there. So the Higgs boson proves the existence of the Higgs field, and the Higgs field gives mass, because of its baseline value of 1 rather than 0. And that is what mass is.